Hitting a high thermal conductivity target on a pristine datasheet is incredibly easy, but chasing that single metric creates a trap, masking the microscopic fractures and physical degradation that will ultimately tear the interface apart. The moment a developer forces a polymer to meet an isolated thermal target, the physical toll becomes brutal. To reach those numbers, liquid polymers are suffocated under massive, dense volumes of jagged filler particles.
OnlyTRAININGS. Learn what works in the industry.
Viscosity immediately shoots through the roof, turning a flowing liquid into a cement-like paste that completely destroys dispensability. What remains is a crippled structure riddled with gaping air voids and peeling edges, the hidden nightmares of formulating thermally conductive adhesives. Because getting the conductivity higher is only half the problem. The real difficulty starts when the material hardens into a useless block before it ever leaves the storage shelf. Modern hardware offers no room for error, placing intense, concentrated thermal loads onto tightly packed semiconductor packaging and extreme heat EV power modules. These environments demand that thermally conductive adhesives and TIMs for electronics simultaneously deliver flawless electrical insulation, a low modulus, and micro-thin bond lines. Attempting to force these opposing properties into a single formulation through trial and error quickly leads down a path of sudden failures and dead ends. Treating rheology, adhesion, and reliability as separate subjects guarantees that fixing one parameter will violently crash another. Thinning the material out causes the heavy particles to settle, while tweaking the chemistry leads directly to catastrophic pump-out during thermal cycling. This cascade of compromises creates massive internal mechanical stress, literally tearing delicate electronic components apart from the inside as they expand and contract. To stop the cascade, you have to look past the macro failures and dig into the deeply buried microscopic variables triggering the collapse. Fundamental polymer chemistry clashes constantly against diverse raw filler materials. Distinct particle morphologies, complex size distributions, and subtle surface treatments grind against each other under intense pressure. Unless a formulator understands exactly how all these variables interact simultaneously, their materials will continue to fail under real-world dispensing conditions. Escaping this trap requires pulling those chaotic nodes into a structured, unified pathway. The complex interactions between filler engineering, polymer matrices, and high-loading rheology can be actively mapped, controlled, and optimized. And there is a definitive methodology to finally break the trial and error loop. Master the polymer filler interface, achieve flawless dispensability, and unyielding reliability. Join the Advanced Thermally Conductive Adhesives Formulation training. Register now and build a better thermal formulation window.